We are at Lake Stechlin, and I have the pleasure to have a wonderful group of limnologists out on the lake today, an excursion of SIL 100.
Lake Stechlin is located in northeastern Germany and is a world-renowned site for limnological research. This is because of a long history of detailed monitoring and observations, now combined with experimental studies at the replicated mesocosm facility LakeLab. Like many other hard-water lakes, the surface waters of Lake Stechlin develop a turbid, chalky green or turquoise appearance in late summer. This is due to the precipitation of calcite, crystals of calcium carbonate, that scatter sunlight and thereby reduce the clarity of the lake. These suspensions of carbonate particles are referred to as lake whitings, and spectacular examples are known from many other water bodies, including the Laurentian Great Lakes of North America. The seasonal production of these light-reflecting particles is the most visual reminder of the importance of the inorganic carbon complex in freshwater ecosystems. The dissolved forms of inorganic carbon are carbon dioxide, bicarbonate, and carbonate. These forms are in equilibrium, and their relative concentrations determine the pH of the water. At equal concentrations of CO2 and bicarbonate, the pH is 6.43, while at equal concentrations of bicarbonate and carbonate, the pH is 10.43. Therefore, when more CO2 enters the water, pH declines. This CO2 effect can be simply demonstrated by blowing into a beaker of water and tracking the changes in pH with time. The drop in pH is caused by the transfer of CO2 from the blowing air stream to the water. And as the CO2 dissolves in the water, it hydrates to form carbonic acid. The carbonic acid then dissociates, releasing hydrogen ions observed as a drop in pH. Ocean acidification is a planetary example of this CO2 effect on pH. In a lake water in equilibrium with the atmosphere, the partial pressure of CO2, PCO2, in the water will equal that in the air. However, the actual concentration of dissolved carbon dioxide, CO2 in micromoles per liter, is determined by Henry's law, where the coefficient Kh depends on temperature. Air equilibrium concentrations of dissolved CO2 therefore decline markedly with increasing temperature. In practice, however, large deviations from these air equilibrium concentrations can occur as a result of geochemical and biological processes. For example, CO2 can gradually accumulate in stratified bottom waters due to bacterial respiration, as observed here in Lac Croche, a softwater lake in southern Quebec, Canada, where CO2 in the hypolimnion gradually rises over summer to maximum concentrations that are more than 15 times higher than equilibrium values with the atmosphere. Just as in the laboratory demonstration, this increased CO2 causes a pronounced increase in hydrogen ion concentrations, thus drop in pH in the bottom waters of the stratified lake. Conversely, carbon fixation by photosynthesis can reduce the concentrations of dissolved CO2. This CO2 removal drives the equilibria to the left, with consumption of hydrogen ions and thus a rise in pH. In lakes with intense algal blooms, this drawdown of CO2 can result in extreme increases in pH. For example, to pH 9.3, in this hypertrophic lake during blooms of cyanobacteria in late summer. In addition to gas exchange with the atmosphere and the processes of photosynthesis and respiration, several other processes can remove or add CO2 to lakes and rivers. This includes groundwater inputs, where the CO2 is accumulated from rock weathering as well as from bacterial respiration. CO2 concentrations around 1,000 micromoles per liter can be commonly found in streams where they first exit the ground. The most extreme values of CO2 occur in the bottom of deep lakes with underlying volcanism. A spectacular example is known from Lake Nyos, a crater lake in West Africa, where CO2 from volcanic vents beneath the lake accumulates to more than 100,000 micromoles per liter in its bottom waters. Eruption of CO2 from these deep waters in 1986 caused the asphyxiation of 1,700 residents in a nearby village. Today, a siphon system is used to reduce this risk by continuously degassing the deep-water CO2 to the atmosphere. Volcanic waters, such as Crater Lake in the central North Island of New Zealand, are usually highly acidic. This low pH is due to strong mineral acids, particularly sulfuric acid, entering the lake through geothermal vents. Less extreme acid environments occur naturally in peatland bogs, where cation exchange by sphagnum mosses can acidify the water to pH values below 4. Most freshwaters, however, lie in the pH range 6 to 9, and their dissolved inorganic carbon system is dominated by bicarbonate. The bicarbonate ions that enter lakes and rivers are mostly derived from chemical weathering of carbonates, limestone and dolomite, and silicate rock in the catchments. And there are large regional differences in the importance of these two pathways. For example, the Seine, Rhone, and St. Lawrence rivers are more than 90% dominated by carbonate weathering, while the Amazon River, the world's largest river by discharge, is about 60% silicate dominated. Carbonate is the third form of dissolved inorganic carbon, DIC, and can also enter lakes from upstream and from groundwater. Carbonate can occur at high concentrations in alkaline soda lakes, which commonly have pH values in the range 9 to 10. However, calcium carbonate is not very soluble, and in high DIC waters can precipitate out as the particles of calcite that produce whitings. This precipitation often occurs in late summer, favored by higher photosynthesis, drawdown of CO2, and thus a shift to higher pH, reduced calcite solubility at higher pH and at warmer temperatures, and microbial effects such as organic exudates that enhance precipitation. The equilibrium reactions of the inorganic carbon system give rise to the buffering capacity of natural waters, referred to as acid neutralizing capacity or alkalinity. Acid neutralizing capacity is the capacity to neutralize strong inorganic acids, and is formally defined as the amount of acid required to convert all of the DIC to CO2. Dr. Yves Prairie is a professor of biology and research chair at the Université du Québec à Montréal in Montreal, Canada. He has a special interest in the biogeochemistry of carbon in inland water ecosystems, and here describes the close interrelationships among properties of the inorganic carbon complex.
The inorganic carbon complex in lakes is really composed of three main concepts: dissolved CO2, pH, and ANC, the acid neutralizing capacity that we sometimes refer to as alkalinity. Well, these three concepts are not only fundamental, they are completely interlinked. So interlinked that I think of them as a trinity. If you know any of the two, then there's only one possible solution for the third one.
Carbon dioxide gas is considered a master variable in limnology because it plays so many key roles. It connects the inorganic and organic carbon cycles through primary productivity and respiration. It controls pH and thereby also affects whitings and water clarity. And it connects inland waters with their overlying atmosphere. Carbon dioxide is also a dynamic variable that is subject to large variations in space and time, as Dr. Yves Prairie here explains.
CO2 is this master variable, but it is far from being constant. In our landscape, in our Canadian landscape, where lakes are typically frozen for part of the year, right after ice out, we will see a big burst of CO2, and then it will gradually decline. And this burst is because the CO2 has accumulated under the ice over the winter months. And when the ice breaks out, this CO2 that was accumulated is now liberated to the atmosphere. And then throughout the season, it'll go down at first and then will climb up again, depending on the metabolic balance between respiration and primary production. And this we can see even on a diurnal cycle. CO2 will typically go up and down diurnally simply because of this cycle of primary production during the day and respiration going on at night. In stratified lakes, typically CO2 will accumulate in the bottom waters because it is isolated from the surface water because of the thermal stratification. And there we can find at the end of the summer very large concentration of CO2 accumulate.
The surface waters of most lakes, rivers, and streams are supersaturated in carbon dioxide. And so there is a constant net efflux of excess CO2 from inland waters to the atmosphere. This excess CO2 and the resultant flux derives from the inputs of CO2 in groundwater from the watershed, and also the excess of respiration over primary production within the lake or river, net heterotrophy, that is due to the metabolism of terrestrial carbon inputs to the water. The CO2 in surface waters is therefore an integrated variable that reflects lake, river, and catchment processes, as well as determines the magnitude and direction of exchange with the atmosphere.